Today we're going to be working on implicit differentiation using what we know about your derivative of exponential functions and logarithmic functions. So see if you can pause the video and come up with your own ideas to start. I'm going to show you the answer keys so you can see where you went wrong or right. All right, so let's get started. We'll start with just doing these quick implicit differentiation exercises. Now with implicit differentiation, right, we're going to take turns deriving each variable. So you'll notice that we need the product rule here. And at this point, if you're at this point in your class, more likely than not, you're not breaking these up and you're just going to go right for it. If you still need to break these up using the product rule, quotient rule, and so forth, just take your time with it. So here we have the derivative of x, that's 1, e to the y, plus x. Now the derivative of e to the y is e to the y, and that's completed, right? And then your chain rule, if you wanted, you could say this is 1. But now we get to tack on your dy dx. That is the implicit differentiation. We're saying, hey, this derivative of y is really going to be in terms of x. So that's the derivative of that first term. Now we can move on to your second. And your third, again, dy dx here is equal to 0. Now, if that is all you need, that's great. More likely than not, they're going to ask you to then solve for dy dx, in which case we need your dy dx values to be on one side of your equation and everything else can be moved over. So that means we are going to keep this on one side. That 10 can move over, and then we'll subtract the e to the y over. Now, because you have two of these dy dx's, to go from 2 to 1, we get to factor out your dy dx. Then you're left with x e to the y plus 3. Now that there's one of them, we can go ahead and divide by your parentheses. And there you go. And no, these e to the y's do not cancel like that. They would all have to have that in common. But that is your implicit differentiation. So let's try it again with 64. Now 64, this first term, you might want to consider breaking it up just to start if you're not comfortable with the derivative of e with an implicit differentiation. So first think about the chain rule aspect. So let's take your outside function and derive it as normal, that is itself, and then take your exponent and then slowly derive your exponent using the product rule paired with your implicit differentiation. So you have x, or the derivative of x, then times y, plus x, now the derivative of y. And now let's put it all together for that first term. So we have e, and normally it would be e to the x, but keep in mind how that chain rule works. We bring these two ideas together and then multiply by the derivative. So we have e to the xy times y plus x dy dx. And now we can move on to your second term. So we have 2x minus your third term, 2y dy dx is equal to 0. So now let's go ahead, as we did from our last example, try to get all of your terms with your dy dx on one side. We might also want to consider breaking this open because it does have parentheses. So let's go ahead and distribute that e to the xy in. Let's see. Minus 2y dy dx is equal to negative 2x. And then let's go ahead and try to get your dy dx's alone to one side. So now that they're alone, we go from 2 of them into 1 by factoring them out. And one last step, dy dx is equal to negative 2x minus y e to the xy all over x e to the xy minus 2y. And there you go. Now I'm going to just do one of these next ones. So I'll do the top one, and then we'll just move on from there. So nice and slow, right? First off, we need your derivative because we're talking about your tangent line here. So let's go ahead and derive. We have x, oops, so sorry. We have e to the y, right? Or 1 times e to the y plus x e to the y dy dx plus dy dx e to the x plus y e to the x is equal to 0. So just as you did with last time, let's go ahead and get these dy dx's alone to one side. We're going to subtract your y value over, and again, this e to the y over. And now let's go ahead and factor out your dy dx. And last thing, let's go ahead and divide. I don't like how I am squishing everything because this part is actually important. So we have dy dx is equal to negative y e to the x minus e to the y all over x e to the y plus e to the x. So sorry, my y looked like a 4 for a second. Now from here, right, we have everything that you need. Well, nearly everything you need, right? You have your x value of 0. You have your y value of 1. That is just your x and your y here. And you might be asking yourself, well, how does this turn into an equation for your tangent line? Well, keep in mind your derivative, right? Your derivative is all about your slope. So what we've just found is portion of your slope. This is the equation to get your slope. So let's go ahead and work in your x and your y. So you have negative 1 e to the 0 minus e to the 1 all over. That would be 0 plus e to the 0. So you have negative 1 minus e to the 1 over 1. So therefore, negative 1 plus e. So this is your slope here. And we want to keep it as exact as possible, right? We don't want to estimate and say this is about negative 3.72-ish, right? So instead, we are going to keep it as is, and this is your slope. So when it comes to y equals mx plus b, right? Or I guess actually in this one, they may have used your point slope. Y minus y1 is equal to mx minus x1. So you have your y, you have your x, right? That is 0, this is 1, and now you have your slope of negative 1 plus e. So we can go ahead and say, okay, this is 1, or y minus 1 is equal to negative 1 plus e to the x, actually e times x. And that would be your equation. And again, if they wanted it in slope-intercept form, move over the 1, distribute, and start to simplify. So that is your answer here. And again, do it one more time just with your next problem, and I'm going to show you your answer key.